Hello everyone, this is Pratyush and my group members include Vasu, Shuvangi and Ronit. As part of our PDC group project, we created this simple website that lets one draw using Fourier transformation and to be precise, discrete Fourier transformations. Let's see a demo. As you can see, whenever I draw something on this black canvas, it gets repeated using a set of circles and vectors. And if you look at this for a longer time, you'll realize that this is simple and both chaotic at the same moment. Let's take a look how this works. The math behind an animation like this is what's known as a complex Fourier series. Each little vector is rotating at some constant integer frequency, and when you add them up all together tip to tail, they draw out some shape over time. By tweaking the initial size and angle of each vector, we can make it draw anything we want, and here's you will see how.
Before diving in, take a moment to linger on just how striking this is. This particular animation has 300 rotating arrows in total. Think about this action of each individual arrow is perhaps the simplest thing you could imagine. Rotation at a steady rate, yet the collection of all added together is anything but simple. The mind-boggling complexity is put into even sharper focus the farther we zoom in, revealing the contributions of the littlest, quickest arrows. Considering the chaotic frenzy we are looking at and the clockwork rigidity of the underlying motions, it's bizarre how the swarm acts with a kind of coordination to trace out some very specific shape. And unlike much of the emergent complexity you find elsewhere in nature, this is something we have the math to describe and to control completely, just by tuning the starting conditions, nothing more. You can make this swarm conspire in all right ways to draw anything you want provided you have enough little arrows. What's even crazier, as you will see, is the ultimate formula for all this is incredibly short. Often Fourier series are described in terms of functions of real numbers being broken down as a sum of sine waves. That's turned out to be a special case of this more general rotating vector phenomenon that we will build up to, but it's where Fourier himself started. And there's a good reason for us to start the story there as well.
Fourier was working on the heat equation when he developed this big idea. And while I would like to talk about Fourier series in a way that does not depend on heat equations, but if you have at least a high level idea of the problem from physics which originally motivated this piece of math, it gives some indication for how unexpectedly far-reaching Fourier series are. All you need to know is that we had this equation describing how the temperature on a rod will evolve over time, which incidentally also describes many other phenomena unrelated to heat. And while it's hard to directly use it to figure out what will happen to an arbitrary heat distribution, there's a simple solution if that initial function looks like a cosine wave with a frequency tuned to make it flat at each endpoint. Specifically, if as you graph what happens over time, these waves simply get scaled down exponentially, with higher waves decaying faster.
So, the heat equation happens to be a linear equation, meaning if you know two solutions and you add them up, that is sum is also a new solution. You can even scale them each by some constant, which gives you some dials to turn to construct a custom function solving the equation. This fairly straightforward property is incredibly important. It means we can take our infinite family of solutions to these exponential decaying cosine waves, scale a few of them by some custom constants of our choosing, and combine them to get a solution for a new tailor-made initial condition, which is some combination of cosine waves.
Something important I want you to notice about combining the waves like this is that because higher frequency ones decay faster, this sum which you construct will smooth out over time as the high frequency terms quickly go to zero, leaving only the low frequency terms dominating. So in some sense, all the complexity in the evolution that the heat equation implies is captured by this difference in decay rates for the different frequency components.
It's at this point that Fourier gains immortality. I think most people normally at this stage would say, well, I can solve the heat equation when the initial temperature distribution happens to look like a wave or a sum of waves. But most real world distributions don't at all look like that. For example, let's say you brought together two rods each at some uniform temperature and you wanted to know what happens immediately after they come into contact. To make the numbers simple, let's say the temperature of the left rod is 1 degree and the right rod is minus 1 degree and the total length L of the combined rod is 1. Our initial temperature distribution is a step function that is so obviously different from the sine waves and the sum of sine waves. And yet Fourier thought to ask a question which seems absurd. How do you express this as a sum of sine waves? And even more boldly, how do you express any initial temperature distribution as a sum of sine waves?
And it's more constant than just that. You have to restrict yourself to adding waves that satisfy a certain boundary condition, which means working only with these cosine functions whose frequencies are some whole number multiple of a given phase frequency. And by the way, if you were looking with a different boundary condition, say that the endpoints must stay fixed, you would have different set of waves at your disposal to piece together in this case, simply replacing the cosine functions with sines. It's strange how often progress in maths look like asking a new question rather than simply answering an old one.
Fourier really does have a kind of immortality with his name, essentially synonymous with the idea of breaking down functions and patterns as combinations of simple oscillations. It's really hard to overstate just how important and far-reaching that idea turned out to be, well beyond anything Fourier could have imagined. If nothing else, this should give a hint of how generally applicable the Fourier series are. Just to put it out there, the Fourier series can be explained as expressing a repetitive curve as sum of sine curves. Since the summation of sine waves interpretation shows how many of waves there are at each frequency, it is widely used in engineering, physics, and mathematics. The main idea in this interpretation is that sine and cosine functions are mutually orthogonal, like vectors which are perpendicular to each other, and a Fourier transform is a mathematical transform that decomposes functions depending on space or time into functions depending on the spatial frequency or temporal frequency. Now let's take a look at a Fourier transformation of a square wave.
A square wave is represented by this function L, which is the period of fx, is 2 pi for this example. Now I will show that what happens to the sine wave when we keep on increasing the value of n like this, that is 1, 3, 5, 7, 9, 11, 13 and 15. For the square wave signal, adding more terms means turning circles with a smaller radius around the former circle with higher speeds. The frequency of these turning circles is increasing in odd numbers. As we add more circles, that is more n's, we get closer to the function that we started with, Fourier transformation. This is very useful in audio processing. So let's say we have some arbitrary sound wave, and it has a really high pitched awful screeching sound in it. To filter it, we could take this sound pattern and break it into a bunch of smaller sound waves, a bunch of sound waves that have a varying amplitudes and frequency, and then we could sort of removing the one that has the high pitched sound in it and then add them all back together and get a new sound wave.
So now suppose we do something on the canvas. The drawing is on a 2D plane, so we can say that the drawing is made up of points, a series of x and y values. Now from the series of values we can create two lists, one having a series of x values and the other having a series of y values. Now we can say that this series of numbers in a list represents a wave pattern. Each wave pattern has a particular frequency. Frequency meaning how many cycles does it repeat within 1 unit of time. It also breaks it down into, so there's different frequencies, but there's also different amplitudes and different phases. It breaks it down. We can visualize those wave patterns as rotating circles, and these circles are called epicycles. This is done using discrete Fourier transformation and using this formula. And when we apply the Euler's transformation to get this one is easier to understand. We can see that this equation takes the help of complex numbers. So given a list of points, we have to generate another list of points using this formula. But the real challenge was for us to code this purely mathematical formula. So this is how it boils down.
For drawing given a list of x's and y's, we pass them into the DFT function that we created. This DFT function returns real values, imaginary values, frequency, amplitude and phase for each of the values in the list. The frequency, amplitude and phase are for the vectors and epicycles. Now the returned value are again used for finding the origin of the vectors using this formula. And the head of the series of vectors when traced recreates the values. We do the same for the y-axis values, plot the intersection points of both y and x and y, and we get our original drawing back. Okay, so now the question arises how we can do this redrawing of the drawing using only one set of epicircles instead of two. For this, in this formula, we can treat the x sub n as a complex number and multiply it with the cos and the sine terms and get this as the resultant. Now, this updated formula will allow us to input both x and y values of a point and get the frequency, phase and amplitude for the epicircles and the vectors using the same DFT function. The DFT function in our code is updated accordingly. And this is how we use Fourier transformation to redraw our drawings. Thank you.